So the first speaker is James McCall from North Carolina State University. You should be able to share your screen now, James. He will talk about compliant actuators for hand exoskeletons. Please.
All right. Hello, I'm James McCall, and I'm speaking on compliant actuators for hand exoskeletons. We are developing soft actuators for assisting in finger extension in hand exoskeletons. We're focused on finger extension because many neurological patient populations are able to flex their fingers, have difficulty with extension. Soft actuators are desirable for this application due to their high compliance and low weight. Unlike other exoskeletons, where our actuators are placed on the palmar side of the hand to reduce joint contact force and maintain a low profile, this palmar placement increases the need for very high compliance and low passive bending force. This image shows a previous prototype with actuators made of polyurethane. This prototype has some difficulties with chamber kinking during flexion and manufacturability, which is why we're developing elastomer-based actuators now. SolidWorks simulations were performed for 24 actuator designs, created from a combination of 4 cross-sectional shapes, 2 materials, polyurethane, or Dragon Skin 20, elastomer, and 3 different ribbing configurations: no ribbing, hollow ribbing, and solid ribbing. The intention of the ribbing was to decrease actuator kinking during flexion, which might affect pressurization during use. Each actuator design was deflected to an angle of 30 degrees. The minimum chamber diameter and air flow rates were measured to determine if narrowing at the bending point would affect pressurization. And deflection force was measured to determine the passive bending resistance. Each design was then pressurized to 10 psi, and the extension force at the tip of the actuator was measured. The rectangular and semicircular cross-sections gave the highest tip extension forces and lowest passive bending resistance compared to the other cross-sectional shapes. And the actuators made of Dragon Skin 20 had a tip extension force about 30% higher than those made from polyurethane. It was determined that hollow ribbing successfully decreased narrowing of the actuator channel during bending and decreased passive bending resistance. However, it also decreased flow rate by almost 50%. Based on the simulation results, we fabricated 4 Dragon Skin 20 rectangular actuators of different wall thicknesses using 3D printed mold components. The primary blind tube of the actuator was formed in a 2-part cavity with an insert. This assembly of the cavity in 2 parts allowed for easier demolding of the especially thin actuators, and the addition of screw holes at the top of the insert allowed for extrusion of excess elastomer during insertion into the cavity. For these initial actuators, we were unable to degas our elastomer mixture prior to molding the actuators, which caused bubbles to be present in the material. The top left image shows a typical section of cured elastomer with no degassing. The bottom left image shows elastomer which was degassed prior to curing and from which bubbles are completely absent. The bubbles commonly reach diameters of approximately 1 millimeter. They do not appear to affect the function of the thicker walled actuators. The 2 thinner walled actuators did develop pin leaks during testing. Another fabrication issue was inconsistent chamber wall thicknesses due to improper insert positioning. You can see in the figure on the right, as you go along the length of the actuator, the left actuator wall increases in thickness as you go along, and the right actuator wall decreases. This was due to improper positioning, which is caused by some issues with fabrication during 3D printing, or flexibility of the insert, in other cases due to imperfect, non-obvious seating issues in the mold cavity. Actuators were tested by attaching them to a jointed fixture. The individual was placed into contact with the load cell. Each actuator was then pressurized to several different pressures, positioned at joint angles of up to 75 degrees. The figure on the left shows that the thinner walled actuators had lower passive bending resistance and also produced higher tip extension forces across the entire range of joint angles. The superior performance of the thin-walled actuators at producing extension forces at low pressures is highlighted in the figure on the right, which shows that the thicker walled actuators do not begin producing significant active extension force until about 35 kPa or higher. Our results indicate that if we want to minimize passive bending resistance and maximize extension force, we should keep our actuator walls as thin as possible. And because bubbles in the elastomer impact the integrity of thin-walled actuators, degassing during the fabrication process will be necessary. Further reduction of passive bending force is necessary, then the SolidWorks simulations indicate that adding hollow ribbing may help. Additionally, because our mold design led to uneven wall thicknesses, mold insert retention features we placed at the top and bottom of the cavity to secure the insert at both ends. Future testing will include testing the operational bandwidth of these actuators and the robustness of them, as these will be impacted by minimizing the wall thickness. Thank you.
Thanks, James. That was spot on time, 4.5 minutes. Thanks a lot. I give you a virtual applause as well from everyone.